Good afternoon. It's my pleasure to introduce Daniel Szoke, who works with Sentry, previously on Python and now with Rust. So let's hear a little bit about Rust.
All right, so I'm here to tell you about why you should learn Rust as a Python developer. And so, as was already mentioned, I'm a software engineer at Sentry, and I've been working there for almost 3 years. When I started out there, I was originally one of the Python SDK maintainers. Nowadays, I'm the maintainer of our Rust SDK, and I had learned Rust at Sentry as a Python developer in order to be able to take over maintaining some projects that were written in Rust. And so I kind of want to share sort of some of my favorite things about Rust and why I think it's really beneficial for you as a Python developer to learn it, even if you're, unlike me, not going to switch over to Rust more completely. So let's get straight into it. This is kind of the outline I have for the talk. So first I'm going to, at a high level, sort of talk about the differences between Rust and Python, then introduce some of my favorite features of Rust, which include the safety and reliability guarantees and the tooling in Rust. And then lastly, I'll just come back to why I think it's a really good language to learn as a Python developer. So I'm going to start off with sort of what I think is the main philosophical difference between Rust and Python, and that's that Rust is going to surface a lot of errors at compile time, which in Python could turn into a runtime error. And so basically the reason why this happens is because Rust, if you don't know, is a language that is, well, first of all, compiled, and it has a huge emphasis on type and memory safety. And because of this, the compiler is going to enforce a lot of invariants that try to keep your code safe so that it doesn't crash and burn when you go to run it. And I'm going to illustrate this with a little example. So maybe you have written some Python code like this, where you have two variables. One of them starts out with none, and the other is an integer, say 0. And then maybe in between, you have some code that normally you'd expect would modify the value of a so that it has an actual integer value. But in this case, for whatever reason, that didn't happen. And then you're going to try to compare the two values. In Python, this could result in a runtime error because you can't compare a none type with a number, and your program would crash, which is possibly not what you intended. So what does Rust do for us here? Basically, you would have to write that code. Sorry about that. That code would have to be written somewhat like this, where you have a set to an option type. The reason you need to do that is because by default, you can't even assign just any value to none. It has to be explicitly defined as an option type. Then you set b to 0. Let's again assume that those values do not change. When you get to this print line statement, you actually won't even be able to compile this code because the Rust compiler already knows that A and B have different types, and these types can't be compared with one another. And so what actually the compiler would force you to do in Rust, if you wanted to write something like that, is to explicitly check that the value A has an actual non-none value. And the way you would do it is like this, where you say if let sum A equals A. That just means if A actually has some value, let's take that value out of it, and then you would run the comparison. So in this case, you would just have skipped over that if statement, and there would be no problem at all. So that's like the main difference between Rust and Python, I would say. Rust forces you to think about a lot of cases where your program could fail up front. It forces you to handle these, and as a result, if your code compiles, you can be fairly confident that it meets a lot of these safety guarantees. And so that brings me to the next section, which is basically to elaborate on some more of these safety and reliability guarantees that we have in Rust. And this is not everything, of course, it's just some of the things that I really appreciate. The first thing I'd like to talk about is explicit mutability. And that's basically the idea that in Rust, by default, all values are immutable. They cannot change after you define them. You have to sort of opt into this mutability possibility. If we have, say, this code in Python where we set numbers to a list, and then we pass that list to some function, and then we try to print what numbers is afterwards, we have no idea what this would output. And that's because, of course, numbers is a list and lists are mutable. So someone could change this list in mystery in some arbitrary way. On the other hand, if we write the equivalent code in Rust, we might write it like this, where we set numbers to a vector containing 0, 1, 2, 3. We pass it as a reference to mystery. That's why we have this and sign. And then we go to print it, and we know for sure that this code will print 0, 1, 2, 3 because the numbers vector is immutable, so nothing that mystery can do can change that vector. Otherwise, the code just simply would not compile. So if you want to be able to mutate something, you would need to rewrite it. So you would need to first of all define numbers as mutable, but that's not even enough to allow mystery to be able to mutate numbers. You also, if you want to pass by reference, need to declare the reference itself as mutable. And that would also require having a different signature for the function, which is why I've named it differently in the second example. But the important part is the @mut numbers, which just says that basically this reference can be mutated by the function that it's passed to. And then this print statement, now we don't know what it would print because numbers could have been changed in some arbitrary way. And I really like this explicit mutability because if you have some types in Rust that you pass around your code, you sort of know when they might be able to change. That's one frustration I have sometimes in Python is I might have like some class or some other object, and I expect some parts of that to remain stable, but you don't really have a way to strongly guarantee that that's the case. Whereas in Rust you do, which I think is pretty nice. And then another concept I kind of just want to briefly touch on is ownership and borrowing. So these are concepts that are kind of unique to Rust, and I think they're maybe the steepest learning curve in a way. So I'm just going to try to give you a little overview of how it works. But basically it allows Rust to ensure memory safety at compile time and to do this without garbage collection. So you won't have memory leaks because Rust knows when to free variables when they're no longer used. But it can do this without a garbage collector, which means we get a lot of performance benefits. So in order to introduce ownership, I have this little code example where we're gonna define a variable hello, and we're gonna set it to this string hello world. And string from, all you really need to know about it is it's gonna create a heap allocation to store this string, and that's in order to allow it to be mutated, to allow it to grow if needed. So that's why we have this here. And if any of you are familiar with a language like C, if you allocate on the heap, you would use something called malloc, and you would need to remember to free the allocation at the end. But Rust doesn't require you to do this. So what's going to happen when you call string from and assign the result to hello is that the variable hello will become the owner of this underlying heap allocation. When we then call hello, or when we then call the foo function and pass hello to it, not by reference, as you see, there's no and sign here, we say that hello is moved into foo. So now foo owns that underlying memory allocation. And let's assume that foo does some arbitrary things with hello, but it doesn't then save hello anywhere else. What's going to happen is at the end of foo, hello goes out of scope and that variable gets dropped. So if you try to run this code as written, it won't compile. And the reason why is because at this line, that hello underlying memory allocation has already been freed if we assume that foo isn't storing it anywhere else, or possibly if foo does something with it, like store it in some static variable, it might still be there, but we don't really know. It could have outgrown the originally allocated space and been reallocated. In any case, the caller no longer owns hello, so we can't do this. So how might you fix the problem? The compiler might suggest, for instance, that you clone hello. What that basically just does is that it will create a brand new memory allocation that contains the same hello world string, and then it'll give that to foo. So then the hello variable here, its ownership doesn't get transferred. We can still use it to print it out there. Another fix you could do is with borrowing, which is this passing by reference thing that we saw earlier. That would potentially require a different function signature. In the first one, we take a string, capital S, that's the owned type. And in the second one, we take this borrowed str type. So borrowing is a very powerful thing in Rust because it's basically a way that we can share data in different places. We don't need to always transfer ownership. We can have the same underlying allocations used in different places, and that can be quite useful. But there's also rules around it, of course, because in Rust there's a lot of rules. So borrowing basically is the thing that lets us share data with another part of the code without transferring ownership. So what's important here is that the owned data always have to outlive the borrows, because the borrows are basically a reference, and those references need to stay valid for the entire duration that those references exist. So we've got two different types of borrows in Rust, and this is, again, this example that we'd seen earlier with the mystery function and the mutable numbers vector. We have the immutable version where we know numbers will stay the same, and the mutable version where it could change arbitrarily. And these are two different types of borrows, and you can always borrow immutably or mutably as long as your variable is defined as being mutable. But what if you want to have multiple types of borrows? That's where it gets a bit interesting, because so multiple immutable borrows are totally fine. And in this case, now we have two borrows. We have the original numbers vector, and then we're going to do this little thing here, which basically just says, take the first two values in numbers, and I want a reference to them, an immutable reference, because that's just a normal and sign. Then we're again going to borrow numbers on this function call line. That's the second borrow. So mystery gets access to the full vector. But then on this last line, we just want to print those first two numbers that we had extracted earlier. So this is totally fine because, of course, the mystery function can't change numbers in any unexpected way that would invalidate our assumption that numbers is going to remain unchanged and that reference is going to remain valid. But you can never have a mutable borrow and an immutable borrow at the same time. So if we slightly change this code where we still have the same immutable borrow we had before, but now we're passing numbers as a mutable reference to this mystery function, this can't compile. And the reason is, well, first, numbers, like these first two numbers might have changed because mystery mute has the access to mutate those. But even worse, it could grow the vector to a point where it needs to be moved to a different underlying allocation, or it could be shrink so that those values aren't part of the vector anymore, and that would be undefined behavior. And Rust does not like undefined behavior, so that's a big no-no in Rust. And for the same reason as we see here, we also can never have multiple mutable borrows. So Rust basically enforces you can either have as many immutable borrows as you want, or you can have one mutable borrow. And that's just how it is in Rust. There are, as you get a bit more advanced, some constructs that allow you to kind of get around this with runtime checks, but that's a topic for another talk, I guess. And then the last thing I want to mention of the safety guarantees is fearless concurrency. And this is really cool because if you've ever tried writing concurrent code, you might know that there are all sorts of data races you can have, and it's very easy to get into a state where you might have some weird bugs and you don't really know how to reproduce them because they only occur sometimes. Rust has this concept of fearless concurrency, which basically means that the compiler can check anytime data is being shared between threads, and it will force you to use types that safely synchronize the cross-thread sharing so that at least you won't have data races and some of the more simple concurrency bugs. So that's pretty cool. But the next thing I want to talk about is Rust's tooling, because I think this is really helpful both if you're starting out to learn Rust, and also I think more recently it's very helpful if you're doing agentic coding, because the compiler, the linter, and the formatter provide really good feedback for coding agents to help them to get the Rust code to compile. So let me just give an example of a compiler warning. If we go back to this same example of the two mutable references, or sorry, in this case, it's an immutable and immutable reference. The compiler is going to give you an error message like this, which very clearly lays out what the problem is. And I believe it might also, in this case, have like a little note of what you might do differently to resolve this, but I'm not 100% sure. Definitely very often the compiler will give you a little hint of like, hey, maybe you meant to do this. And so that's really helpful if you're starting out with learning. And it's also really helpful if you're a coding agent and need to get the code to compile. The agent very quickly understands, oh, this is wrong, and I kind of know what I would need to do to resolve the situation. Another thing I like about Rust is the linter, which kind of helps enforce best practice. There's a lot of rules in it by default. So for instance, it would help us to simplify this function. If you see, we're basically just having a condition and then returning true or false. The linter will say, hey, you could just return the condition. Yay, so that's a lot simpler. But then it'll also tell us that actually you don't need this return statement and you don't need this semicolon, and that's because in Rust, the last line of a function that's not followed by a semicolon is the return value. So even if you didn't know that, the linter would just tell you, and in a lot of cases it can even just apply the fix automatically for you, so you don't even need to go manually edit stuff. So that's pretty cool, I think. So these are just some of the standard lints, but there's also a bunch of other lints that are like, some of them are kind of best practice, but a bit noisy sometimes. Some of them are just personal preference things that you can opt into. And again, I think these are really helpful if you're coding with agents or with new contributors, because you can enforce the best practice the way you want it and people get immediate feedback. So that's very nice. And you avoid disagreements in code review, which is also always a good thing. And then lastly, we have Rust format, which is sort of the standardized formatter. Almost every Rust project uses it. And as a result, code tends to be formatted pretty consistently in Rust. So as an example, if you had this kind of poorly formatted function, Rust format would just automatically fix it like that. But it's also an opinionated formatter, so it has sort of defaults for how you put the function braces and how you line up the arguments. I mean, I guess in Python we don't even really have the braces, but I don't know. In languages that have them, some people have opinions on this, but yeah, Rust compiler just says this is how you do it, and yeah, again, no disagreements in code review. And even though coding agents, I would say they've gotten better, but they sometimes fail to compile Rust code the first time. I think this is a really good feedback loop for them because they can compile relatively quickly, get the feedback, make the adjustments. And then when you're done, you have code that is guaranteed to meet at least some basic safety principles. So you can be confident that a lot of bugs you might have in other languages won't be present. So that brings me kind of to the point where I want to tie this all together, why you as a Python developer should learn Rust. And I think the first thing is both languages have advantages and disadvantages, and when you know both languages, you can optimize your usage of them by your use case. Rust is really good when you need good performance, when you need code to be reliable, or also it's good as a systems programming language. You need to put in some more upfront effort sometimes, but the result is fewer bugs. Python, you might be able to iterate quickly. It's really good for just some simple scripting, and also for data science, it's amazing due to all the libraries that are out there. But that comes with the cost, which is that sometimes you need some more maintenance effort because it's easier to make mistakes. Then the second thing I think that's really important is that if you learn Rust, you're going to become familiar with the safety concepts that Rust enforces, like null safety, making sure you're handling all the cases, and considering mutability when sharing data. And so when you start thinking about these in Rust, I think that you kind of have that habit that you'll continue thinking about them when you write Python code. And that's super important because, in fact, even potentially more important when you write Python code than when you write Rust code, because in Rust, you have the Rust compiler that's watching out for you. But when you write Python code, you don't have that. So you really need to be more careful with how you're writing your Python code. And then the last thing is, basically follows from the previous one. I think learning Rust, and in general just learning other languages, it will improve your Python skills as you see sort of the different perspectives. So even if you never write Rust again, I think it's worth it to learn a little bit. And so if I've convinced you, my recommendation for learning Rust is to check out the Rust book. I think it's officially called the Rust Programming Language or something like this. It's just the default tutorial, basically. It's online for free. The examples are really good. It explains all these concepts really well. So definitely check it out if this is sounding interesting to you. And yeah, that's my talk. So if anyone wants to ask any questions, you may do so now.
Yeah, thank you very much for that talk. I guess I was just wondering, as a person who switched over from Python to Rust, I guess some time ago, as you mentioned in the beginning of your talk, could you also speak a little bit about any of maybe the mistakes or missteps that you would like other Python programmers to know about before they try to dive into Rust?
That's a good question. I don't know. I don't feel like I hit any super big bumps. And I think part of that is that the compiler really will just tell you when you did something wrong and you kind of get the instant feedback. I'd just say you need to be ready to use different idioms, because things that work in Python, like maybe trying and accepting something when you don't know it will succeed, that pattern doesn't really work in Rust. You always have to check first if something is safe to do, and then you can do it. So I would just say to be open-minded as you continue with that. Yeah.
Okay, thank you.
What's the infrastructure look like for integrating Rust and Python in the same code base?
I'll be honest, I'm not that familiar with it because when I transitioned to Rust, I was working on a separate project. But I've heard of PyO3. That would be like, I'm sure there's other talks on PyO3, but that would be what I would search for to learn about it.
All right, and we can take one final question.
A lot of times you hear that, it's fast because it's written in Rust, but are there design patterns or principles that are portable back to Python that we should be using to make more performant Python in the same way?
That's a good question, and also not an area I have much familiarity with. But perhaps something you can do is, again, as the previous question was wondering, like if you have something that's very CPU bound, maybe you could consider writing just that portion into Rust and having the Python bindings. But again, that's not an area where I'm super familiar with. So
Thanks.
yeah, you're welcome.